Hello everyone and welcome back. In this module we will be putting all of the hard work we've been doing into action by doing some actual statistical modeling. Because really the whole point of learning how to do R programming and learning statistics is to analyze data. So that's what we're going to do here. We're going to look at two different data sets. First is the Ames housing data, which you've gotten a bit of a taste of in previous videos, and the other we're going to look at the Titanic data, and we're going to do multiple linear regression on the Ames housing data and logistic regression on the Titanic data. Okay, and we're going to be using dplyr, so I'm going to go ahead and load that package, and I'm going to read in the Ames data. There'll be links to this data set in the description. In my system, from my current working directory, to get to that data set, I have to go up one directory, down into the datasets directory, and then grabs ameshousing.csv. Okay, so let's take a look at the data. This is a data set with home sale transactions in a city called Ames, Iowa, for about 5 years. I believe it's 2000. Well, let's just check. Table Ames dollar year sold. Tables. Table. 5 years, 2006 to 2010. Okay, and here's the data set. There's various, each row represents a house that was sold in Ames, Iowa. And then there's various columns containing attributes of the house. So lot frontage, that's like how much of the street the lot takes up. Area, type of street, type of lot, utilities, neighborhood we're going to look at. Because of course location is important in real estate. Type of building, house style, overall condition is important. The age of the house, basement attributes, size. The size of the house is important. So in this data set, it's broken up into first floor, second floor. GR live area, I believe, is the total living area above ground. Number of full bathrooms, half bathrooms. Full bathroom has like a shower or a tub. Number of bedrooms, total rooms above grounds, garage information, pool information, year it was sold, sale type, sale price. So this is going to be our response. And this is the price in dollars. Okay. So let's just make a histogram of the price. So that's going to be our response. It's important to, just take a look at the data. Whenever you're analyzing data, you really need to find a way to look at it to get a handle of what's going on. So here's just a histogram of the sale price. This looks like a kind of a standard distribution of something like home prices or something like income. It tends to be skewed to the right. One of the most important variables is the size of the house in terms of how many square feet it is. And here's just a scatter plot of those two. This is the size on this axis, the price on this axis. You can see generally as you increase the size, the price goes up. Now, the thing that kind of pops out here is that there are these three outlying houses. So how do you deal with outliers? Well, it really depends on why they're outliers. If there's some attribute in the data set that can explain this, well, then maybe we could just add that attribute to the model and then everything will be fine. However, you really got to look at them. And if there's only a few, we can do that pretty easily. So what I'm going to do is to investigate these outliers, I'm going to take all the data that are bigger than 4,000 square feet and just look at them. So that's what I'm doing here. And I'm using a pipe, and I'm using dplyr arrange to arrange by sale price. And I'm subsetting here. You know, I really could rewrite this in dplyr mode. Let's do that actually. Well, let's do it next to it. So Ames filter gr live area greater than 4,000. Arrange sale price. Okay, these should give the same answer. All right, let's look at the data. So I've arranged by sale price so that these 3 cheaper houses are listed first. So keep that in mind as we're looking at the data. These are the 2 more expensive houses. Okay, so lot area. So we're looking for differences between the first 3. Well, first thing is that these 3 have much bigger lots, larger property. They're all in the same neighborhood, whereas these other 2 expensive ones are in, these other 2 large houses are in Northridge. 1 family, it could be 1 or 2 stories. Overall condition, average. Year built. Okay, so this kind of pops out that all 3 of these houses were built in 2007 or 2008. When were they sold? 2008, 2007, 2007. Okay. What I'm starting to wonder is, were these actually sold as properties without a house on them, and then someone went back and filled in the attributes of the house that was eventually built on that property? Because it does say, okay, this is a bit odd. 6,000 square foot basement, 5,000 square foot basement, 3,000 square foot basement. For context, if you're not used to these units, a 3,000 square foot house is a pretty large house in the United States. So to have a 6,000 square foot basement is a bit strange. What else? This one says there's 3,138 square feet on the first floor and exactly the same number in the basement. That's strange. Okay. You know, this is one kind of another weird thing. The sale type is new, and that makes sense because year sold is pretty much the same as year built. However, the overall condition is average. It's kind of strange to say that a brand new house is in average condition. So that's a bit weird. What I'm wondering, like I said before, is that maybe these were sold as properties without houses on them, and then they've gone back later and filled in the attributes. So these are outliers. It seems like probably there's a mistake in the data in that this price does not include the house that was eventually built on there. So I think for the rest of the analysis, I'm going to take these out and not include them in the analysis. Okay, so anytime with outliers, you have to kind of look at them and decide what to do. If you ever sold a automatic outlier detection, you should be kind of skeptical of that. You really have to get your hands dirty and look at the data. Okay. All right, investigating the outliers. This is just to see if maybe this was explained by neighborhood. It is true that Edwards is one of the less expensive neighborhoods, and what was it called? Northridge is one of the more expensive neighborhoods. But even if we subset to Edwards, these 3 houses are still outliers with respect to what a typical sale price in the Edwards neighborhood is. So I think we're safe to remove them. But just to see, all right, so how am I going to remove them? I need to basically find them. So what I wanted to get is all the houses whose living area is bigger than 4,000 and whose sale price is less than $300,000. If I do that, I grab exactly those three houses. Those are them. Where's the sale prices here? And what I'm going to do, just to kind of illustrate the effect of removing or not removing these outliers, is I'm going to fit two models. Very simple models, just has one variable. And one of them I'm going to subset to the not outliers. And the other one I'm going to leave them in. So let's fit those two models. Here's the first one with the outliers in. You could see that the effect of size of the house is $111. So the way you interpret that is for each, what this model says is that for each increase of 1 square foot, you expect the sale price to go up by $111. Okay, so whenever you do this, you got to say like, okay, does that number make sense? So if you increase the size by 1,000 square feet, which is basically for a small house is like doubling it, for a medium-sized house is adding, somewhere like 50% more. It would go up by $111,000. So that sounds, roughly about right for this time period. Okay. If you take them out, it goes up by $118. And this kind of makes sense. And to see why this makes sense, that this number should be higher, let's make this plot again. And then I'm going to add the trend line from the two models. The first one in blue is with the outliers in. And the second one in magenta is taking them out. And you can see that, consistent with the table we just saw, the slope is higher. And so when you leave them in, basically, it has to make this slope a little bit lower to reduce the effect of these outliers. So that's what happens to the model when you leave them in. I think we should take them out because I think that there's something erroneous in the data. All right, let's try to fit some models. So let's look again at the data to try to figure out which variables we'd like to include. Neighborhood we are going to look at, but not initially. Overall condition is going to be important. We're going to skip basement square feet, and we're going to skip splitting up the data to first and second floor. We're just going to look at total size of the house above ground, number of full and half bathrooms, number of bedrooms. We're going to look at number of bedrooms. Total rooms we'll skip. Garage, well, we'll take a look at these, but I think we're not going to put them in the model. Years sold, I don't think I put in the model, but I do want to add that and see what happens. And then our response is going to be sale price. Now, there's certain things in the data that probably we should figure out what they are if we want to do a more complete analysis. For example, sale type WD. I don't actually know what this means. And if you were really wanting to do a good analysis, you'd probably want to figure out what every single variable means, because maybe this is important. But we'll skip this for this analysis. Okay, so those are some of the variables that we think are going to be important. Let's actually take a look at each of them. All right, overall condition, we can see if we just do table on that variable, it spits out all the different conditions, and then it says how many fall into each category. So a lot of them are average, which makes sense. Some are above, some are below. And then there's, various other categories. Good comes up a lot. There's a few very poor, a few very goods, and 7 very poors. Okay, full bathrooms. there's between 0 and 4. We should take a look at what it means for a house to have no bathrooms, because that's a bit unusual, but let's move on. Half bathrooms. A lot of houses have 0 half bathrooms. So the way this is usually indicated is, if you have 1 full bathroom and 1 half bathroom, it will be listed as 1 as full bathroom and 1 as half bathroom, and not 1 is full bathroom and 3 is half bathroom. So this is half bathrooms in addition to the full bathrooms. That's why there's a lot of zeros, because most houses actually don't have any half bathrooms. Total basement square feet. Okay, these are these outliers. There are some zeros here, and that's because some houses don't have a basement at all. Garage area, similar issue. If there's a garage, it's of some minimum size, but if there's no garage, it's just listed as 0. Pool area, there's a lot of zeros. If you really stare, you might see that there's actually some bumps here. I mean, there have to be bumps here because or else it wouldn't go all the way out to 800. If we just do table pool area bigger than 0, most of the time that's false, because most of the time it's 0, but there are 13 houses with a pool. Okay, so let's fit a model with some of these. You know what? I'm going to go ahead and add year sold, which is going to change my code below, but that's fine. Okay. All right, so here's the fitted model. If you do summary, so I'm using the LM function. The way this is used is you do response and then tilde and then all the different variables you want to put in the model separated by pluses if you want to do an additive model. We will do interaction models below. Say which data set you want. So the way the code works is it knows to reference these columns from this data set if you supply the data. Works very similarly to how these dplyr functions work. So filter knows to grab gr live area from Ames, and arrange knows to grab sale price from the output of this thing. Okay, so here's our fitted model. And let's just go through the coefficients and take a look. We have to be kind of careful in how we look at these because it's printed in scientific notation. But I think that's okay. We can figure these things out. Intercept, basically this is what you expect the sale price to be when all of the variables all the numeric variables are 0 and all of the factors are at their baseline level. So 2.059 times 10 to the 6 should maybe throw you off a bit because that means 2 million. And remember when we looked at the plots of the data, none of the houses were that expensive. Basically, there were actually none over 1 million. So that's a bit strange. What's going on there is year sold is 2006 through 2010. So basically, if you set this to its lowest to 0, you're at year 0. So that's like a enormous extrapolation outside of the range of the data. So that's why you get a ridiculous value here. And the reason you get such a big value is because the coefficient on year sold is negative, which if you kind of visualize this over time between 2006 and 2010, prices are going down. And so if you take that downward sloping line and extract it backwards in time, you're going to get a huge positive intercept. Okay, so that's why that number's weird. This number is 83.5. So for each additional square foot, you get $83.5, which is a bit lower than what we saw before. It was 111. Basement square feet, you get less money per square foot of basement. That kind of makes sense. You get $10,000 or almost $11,000 for a full bathroom. You get $13,000 for a half bathroom, which is kind of interesting, that a half bathroom is worth more than a full bathroom. I suspect there's probably something else going on there, like having, a house having having a half bathroom is like a proxy for it being a nice house. So that's why, that's higher. Garage area, you get $70 per square foot. This is an interesting one. Bedrooms above ground is negative. So if you don't think too much about this, you should think, okay, houses with more bedrooms tend to be worth more money. And so it's a bit strange that you get a negative coefficient there. But what you need to remember when you're doing multiple linear regression is that the interpretation of each coefficient is this is the effect of that variable while holding all other variables constant. And an important one in this model is the total size of the house above ground. So GR live area is in the model. So the way you interpret this is if you increase the number of bedrooms without changing any other variable, and that includes the total size of the house. So it's like you're taking a house and cramming in more bedrooms without increasing the size of the house. So if you really wanted to know what's the impact, and that's why it's negative, because I guess that's seen as less desirable if you have a house that's, all bedrooms and no shared living space. If you really want to see the effect of adding a bedroom, you really should say, okay, if I'm adding a bedroom, it's going to be some specific size, maybe, I don't know, like 200 square feet. And you calculate how much that changes all the other variables, including this one, and then figure out if it will improve the cost of the house. All right, years sold is negative. I think, one thing we should look at is to do years sold as a factor. There's two ways of doing that. I'm going to do it the easy way. So Ames dollar year sold. And I'm just going to make a new variable called fac. And I'm going to change this. Okay. So here, this is our first factor in the model. And this makes the output look nicer, so I like this. Okay. This is our first factor in the model. And what you'll see when you put a factor in the model is that the lowest level of the factor, in this case, the year 2006, does not appear. And so the way you interpret these coefficients is this is the change relative to 2006. So 2007, houses sold for a bit less. 2008, a bit more or less. And then, as you might know, there was a big crash in the housing market in the United States around 2008. And so the prices in 2009 and 2010 are actually much lower. So generally over time, home prices go up. But in this specific period, they were actually decreasing because of a housing market crash, which is kind of interesting. Okay. And then you have all these different factors for the condition of the house. And again, because this is a factor, we have to interpret them relative to the baseline level. And here it's not clear what the baseline level. I think they just do it alphabetically, but I forget what all the different levels were. So we can look at overall condition, which is a character vector, convert it to a factor, and then look at the levels. And you can see that the baseline level is above average. So we have to interpret these coefficients relative to above average. Okay, so the first thing you get is, okay, this is a bit weird that average is 8,900 better than above average. So that's weird. And it's significant. So that might require some more investigation. Below average is bad. Excellent is good. Fair is bad. So fair is below good. Good is good. Poor is really bad. Very good is pretty good. And then very poor is very bad as well. Okay, so there is some signal in this condition variable. There's a few that maybe don't make so much sense. This one in particular. Versus above average, but overall I think that this condition variable is useful. Okay, what else to look at? One thing I think that's important is to understand how good is your model, and one measure of that is what is the residual standard error. So this is basically on average when you're using this model to predict home prices, how far off is the prediction, and this says about $37,000. Okay, other things you look at are like multiple R squared. This is the proportion of the variation in the data that's explained by this model. Okay. Another thing you want to do when you're doing this big complicated regression is take a look at the residuals, see if there's anything that stands out. One thing, so the way I grab the residuals is I use this model object, M2, that's the model I fit here. And then there's a field called residuals. So one thing to point out is that the length of this thing doesn't always match the size of the data set. So if you look at that versus number of rows of Ames, they differ by 3. This is because when they fit the model, if there's any missing values in any of the variable, by default what the model does is it takes those data points out. And apparently there are 3 rows with missing values, and so it took those out. It doesn't include that here. So the question is, if you want to make like a plot of residuals against other variables in the model, you have to know how to match them up. But thankfully, in this residual object, it names the each value using the row names from the original data set. And the row names are just numbered 1 through, what was the number? 2930. And so you can do an assignment like this. So I'm gonna add a column to the Ames data frame. I'm gonna call it resids M2. And the rows that I'm going to insert them at are M2 residuals, the names of M2 residuals, and I'm going to put that in there. So basically it's going to skip. Actually, we should do this. We should figure out. All right, let's go through this. So names M2 residuals. And I'm going to say we want to do some operations on these. So I'm going to convert this to a number. So there's save, head, tail. It goes up to 2930, but the length is 2927. So which ones are missing? How would you find that? Well, you could do something like diff. Most of the time this is 1, but it's going to be 2 somewhere. So I could say which diff okay, what happened there? Oh, I said equals. I need to do not equals. Okay, there's two of them. $495, 6, 7, 8. All right, so $14.99 is missing, which means $29.80 is going to be also missing. And let's see. What? Maybe you could see this faster than I can. I don't see which one. Oh, these are these ones that we took out. Okay, that makes perfect sense. These are the three that we took out. There's actually no missing values. These are just the three we took out. So you probably saw that immediately, but that took me a second. Okay, still we can assign them like this. And let's make a plot. So what we're going to do is make a plot of the residuals against some of the variables in the model. And there's the plot. Okay, so these first two, it looks to me, so what you want to see is basically just noise. Like you shouldn't be able to predict, because we put these areas in the model, you shouldn't be able to predict the residuals using those variables because they're already in the model. So if you see any kind of pattern, maybe we should put them in a different way. And on these first two, and maybe even this one as well, it does kind of look like there's maybe a quadratic pattern here. And I think that was, if you go back, that is kind of reflected here. There's a bit of a quadratic pattern. So maybe we could add another term, the square of grlive area. Let's see, we lost our... And the same might be true of total basement. Maybe there's a bit of a pattern here. What else? Oh, the other thing that's, maybe we should deal with is the fact that the variance of the residuals seems to depend on the size of the house. So for these smaller houses, we could say it's easier to predict using this model the size of the house or the price of the house because the residuals tend to be closer to zero, whereas they're more spread out here. There's various ways of dealing with that. You could fit a model, and you could fit a model where the variance changes with one of the variables. You could also take a transformation. So you might take a square root or a log transformation of the price, the very common thing to do to deal with that. And then you just got to kind of look at it and see if the fit is better. The other ones kind of look okay. One thing that's kind of interesting is that if you look at the houses with no basement, they tend to be worth more, meaning positive residuals, relative to what the model predicts. So you might want to put a factor in the model like has no basement to try to improve the fit of those. or a factor in the model like has no garage, which is equal to, garage size equals 0. That potentially could improve the model as well. Okay, but we can only do so much in one video, so we're not going to do that. This we're going to look at to figure out what was going on here. Why is this plotted here, but there's no data? That's because we removed those 3 houses with weird values. So let me get rid of this actually. All right, now I want to look at the neighborhood variable. To keep things simple, I didn't add it to our first model, but as you know, the location of a house is very important to its price. So I'm going to go ahead and add neighborhood. Now, if you do type of Ames $neighborhood, it's a character vector. And just like with overall condition, which is also character vector, R will automatically convert it to a factor when you try to put it in a model. That reminds me, I need to add year sold fac. This is one of the, the fact that it converts characters to factor and kind of deals with them very gracefully is one of the really, really nice features of R. Basically, I don't have to do anything special for that variable. It just knows to treat it as a factor. It knows to create a design matrix with dummy variables. It knows that if you include all the levels as dummy variables, the design matrix is going to be not full rank, and it knows to remove one of the columns. So it knows all that stuff, and it knows how to fix it. So this is one of the really nice features of R. Now, as you recall before, there's lots of neighborhoods. So when I do the summary, it's going to give me this huge table. Okay, so these are all the neighborhoods. And some of the neighborhoods have really long names, which means that the whole table doesn't fit here. So what we're looking at here are the T and P value columns. If we go back up here, now we can see the estimates. I don't know what the baseline neighborhood is, but it kind of doesn't matter because we don't really know what any of these neighborhoods mean. Unless you're from Ames, Iowa, you'll know something about these. Okay, so that's a model with neighborhood. It kind of makes a mess of everything, but it's a perfectly valid model. And what I want to draw your attention to is that for one, many of these p-values are significant. The way you interpret that is that this neighborhood, Somerset, has a positive t statistic, so it's significantly more expensive than whatever the baseline neighborhood is. If we could pick a big one, so this one, Northridge Heights is significantly more expensive than the baseline neighborhood. So there is information in the neighborhood. And you can also see that if you look at the residual standard error, because this is, before it was around 37,000, now it's 31,000. And before, the multiple R squared was about 78%, now it's 84%. So this model with neighborhood does a better job of predicting sale price than one without it. You can also do a formal test of that. So if we just say ANOVA M3, print that out. The last row does what's called an Ftest for comparing a model with neighborhood to one without neighborhood. And the F statistic is very large, 39, which has a tiny p-value. So that this is a formal statistical test for whether the model with neighborhood is better than one without it. And you can see when you do ANOVA on this model, it prints out a whole bunch of stuff. Basically, these, as F tests, these are not interesting. Only the last one is interesting because it's basically comparing a model with neighborhood to one without neighborhood. And in my personal use of the ANOVA function, I actually almost never call it in this way with a single model. I'll almost always call it with the two specific models that I want to compare. And that will just print one line that tells me whether model 3 is significantly better than model 2. And it gives the same exact F statistic as this one. So it does the same exact test, but it comes without all this kind of extraneous information. It just gives me the number that I need. So to not confuse myself, I'll almost always just call this with two models here. Okay. Oh, and this will tell us the baseline. So Bloomington Heights, if you were curious, is the baseline neighborhood. Okay. Another thing I want to look at is a comparison of the coefficients of the model with neighborhood and without neighborhood. And I think I need to change this to 11 since I added years sold. Okay. Am I missing one? Oh, okay. So that has the condition. So I'm just going to leave those out. Okay. So what we're comparing on this column is the model without neighborhood, and on this column is the model with neighborhood. And just to keep things simple, I'm going to leave out the year sold. Okay, let's just look at these. All right, so these are the coefficients for these variables, but in the more complicated model that has neighborhood. And what you'll tend to see when you add a variable like neighborhood, which explains a lot, has a lot of information in that variable, is that the size of the coefficients for all the other variables tends to, won't always, but tends to shrink. So for example, the effect of adding 1 square foot, holding everything else constant, is bigger in the simpler model and smaller in the more complicated model with neighborhood. Basement size, the effect is smaller. Full bath is much smaller. Half bath is much smaller, although it is still larger than full bath. You can always make up a story. The story I made up is that a half bath is actually a proxy for it being a nice house, because you really have to have a nice big house in order to justify having a half bathroom. Effective garage area is smaller, and the negative effect of squeezing in bedrooms is also smaller, or closer to 0. So the reason there why this column the numbers tend to be smaller is in this model you don't have neighborhood in the model, which is clearly an important variable. So what this model, the way I interpret, what it's trying to do is use these variables as like a proxy for what neighborhood it's in. So bigger houses tend to be in better neighborhoods. So you're going to put a bigger coefficient on the size of the house. Houses with lots of bathrooms and half bathrooms tend to be in nicer neighborhoods. Houses with nice big garage tend to be in nicer neighborhoods. So this model, it's like trying to use these variables to predict neighborhood, and that is kind of inflating the size of these coefficients. Whereas here you just have neighborhood in the model, so now you see basically the naked effect of adding size to the house. So that's the way I interpret that. Okay, one last thing here. When we printed out this neighborhood thing, we got all these, it's kind of complicated, the table. One, not a great justification but one remedy for that is to just make neighborhood a random effect. And so let's just talk for a minute about what the difference is. Basically, the way I view having neighborhood as a random effect versus having it as a fixed effect, it's not that you think the effect is random. You hear that said a lot, but that's actually not a good justification in my view. A better justification is the actual assumption is that the neighborhood effects are random and normally distributed in this model. So I think a better assumption or justification for adding neighborhood in as a random effect is that you think the neighborhood effect is the neighborhood effects, like all these numbers in the table, are close to normally distributed. Because that's really what the assumption is. So the way I think about random effects is that you're adding an additional assumption about the neighborhood effects, namely that they roughly follow a normal distribution. So why would you do that? Well, without getting into too much of a rant about assumptions, you make assumptions because they help you in some way. And we go around life making assumptions all the time. So it's not like this is an unnatural thing to do. So why would this help you? It simplifies your table. It allows you some justification for saying, if you add a new neighborhood, or if you had a neighborhood that didn't happen to be in the data set, what its effect might look like. Whereas technically in the non-random neighborhood effect model, you really have no basis for saying what its neighborhood effect will be. Sometimes it can make the model fitting faster if you have a huge data set to make it random effect. But that can go either way. So let's just do it and take a look. By the way, we're using the LMER function to fit the random effect from the LME4 package. The syntax is the same as in LM. So for all the what are called fixed effects, the non-random effects, everything looks exactly the same. But for the neighborhood effect, to tell it that it's going to be a random effect, you do one pipe neighborhood. And this is basically saying you want a different intercept for each neighborhood. And you do it in this syntax to tell it it's going to be a random effect. Okay. And this is the fit. Okay, so it's telling you it's a linear mixed model fit by REML, which is residual maximum likelihood. Some people call it restricted maximum likelihood. That's a model formula. Residuals. And then this part of the output is new. It's telling you what is the variance of those normally distributed neighborhood effects. And probably more interpretable is the standard deviation. So it's about 30,000. And then this tells you the standard deviation of the residuals, which is pretty close to what we got before, which was 31,720. Whereas here we get 31,736. It's slightly higher. I think the reason for that is that here we're imposing that the neighborhood effects are normally distributed, whereas this model above has fewer assumptions on the neighborhood effects, so basically it can fit them exactly. And so you get slightly bigger residuals here. Okay, and these are the fixed effects. But let's put them together. I want to see what they are for the different models. So we have the model, just to remind you, this is the model without neighborhood. This is the model with neighborhood as non-random or fixed effects. This is the model with neighborhood and random effects. Okay, so we already compared these two. So let's now compare this one to this one, because this is non-random, this is random neighborhoods. And what you'll generally find when you convert a fixed factor effect to a random effect is that the estimates don't change that much, but there will be slight differences. So intercept's about the same, effect of size is the same, effect of basement's the same. This one is maybe the most different. I don't have a good explanation for why it goes up. These are still pretty close. These are pretty close. These are also pretty close. So you will get some slight variation here, but generally these are about the same. And in my experience, that's what I find as well. If you change a fixed effect to a random effect or vice versa, you don't change the model that much.